immediately give the floor to Dirk Jansen. So the timing is quite tricky. So we will start directly with a presentation from Dirk, who is head of section at the German Federal Highway Research Institute, BASt, and leader of the BDPave initiative that stands for, as you can see, big data for pavement management and beyond. Dirk, the floor is yours.
Yeah, thank you very much. Thank you very much. I will start now. Just give me a second. Big data and smart data technologies are rapidly evolving and touching more and more areas of our everyday lives. Not only because we have the possibility to use the internet at all the time and in all places. It is obvious that traffic management related issues are at the forefront. Services such as Google Maps navigation, which are able to make decisions based on very accurate traffic flow data, have become an integral part of our everyday lives. However, the underlying technologies and the algorithms differ only slightly from each other. Transfer to other disciplines and subject areas is therefore possible, provided that the technologies can be penetrated and thus adapted. The creation of structures and accessibility to relevant data sources are in the forefront here. The goal of BDPave is therefore to do exactly this for the field of pavement management. We have therefore made it to our mission to bring together experts from the fields of pavement maintenance and big data technologies in order to create added value. Since the focus is on the adaptation and the use of existing knowledge, BDPave is an initiative that helps to manage knowledge and also to generate knowledge. Thus, existing project results are used synergistically and targeted projects are initiated among FIRL members. The aim is to investigate the entire process chain of converting big data into information in order to achieve improvements in asset management. BDPave is only a blueprint for this. The insights and methods gained here will also serve the other disciplines of the FEHRL institutes and the relevant stakeholders in the future. Big data is often understood to mean only an exceedingly large amount of data. In many cases, this is absolutely correct and it makes sense. If you look, for example, at the hours of video material uploaded to YouTube per hour, it is clearly big data. It is equally clear that managing and analyzing this amount of data manually is not feasible at all, and automated is very difficult. So this applies not only to the IT hardware requirements, but also to the algorithms and methods that are used. Let me briefly explain how we understand the term big data. According to this, data can be structured as well as unstructured or chaotic. It can occur quickly and perhaps unexpectedly in quantities, and also have only a short time of real value. Data have different formats and present themselves to us in different ways. It can be precise, but also have a certain value when they are inaccurate. And big data occur in masses, of course. Yet the value of smaller amounts of data should not be underestimated. All of the aforementioned manifestations of data thus have a meaning, even if it is not obvious at first glance. For example, can you do anything with the lateral acceleration value recorded by your car? Probably not, but if you overlay this value with, for example, weather data and times of day and evaluate the data not only from a single vehicle, but from a large number of vehicles at the same location, you can obtain valuable information for identifying road damage and condition trends. Admittedly, this is a simple example where human intelligence is not yet very challenged. However, if you scale this up, both by the amount of data and the number of locations, a handling with our human intelligence and Excel spreadsheets will immediately reach its limits. Artificial intelligence therefore plays a significant role. It is primarily about translating human expert knowledge into algorithms and processes. Following rules, sounding out behavior in borderline areas, and learning reactions from it form the basis of artificial intelligence. The steps for these are mostly similar. First, the existing data must be checked, supplemented, and cleaned. Then, patterns and rules have to be recognized. From this, applicable knowledge can be generated and behavior can be predicted. The advantage here is that limits such as data volumes and data diversity no longer play a role. We must be aware of this and therefore also consider data sources that at first and second glance do not seem to be related to our question. All this is addressed by BDPave. First of all, we make existing expert knowledge and methods tangible and also derive improvement potentials and needs from them. Furthermore, it is about identifying data sources. In doing so, we explicitly look for data we are already familiar with, such as profile data, but we also want to find and understand new innovative data sources. An example for this is floating car data. Accessibility to data sources is a hurdle, both technically and administratively. These hurdles need to be overcome in work package number 3. Since BDPave will differ from the familiar pavement management and trans-European results are to be achieved, failure modes and models have to be defined. The heart is our work package number 5, which is the big data work package. Here, the methods, the processes and algorithms are to be developed that generate a usable output from big data, the so-called smart data. The transfer to test scenarios and the adjustment of the models to them form the conclusion. In the following, I will try to present the contents and the progress achieved so far in more concrete terms. An international survey and expert interviews were conducted to describe existing procedures and identify development potential. It turned out that the data situation on road conditions in Europe is quite good. However, there are data groups such as bearing capacity data and environmental parameters that are less accessible. Data sources that provide information on other assets in the context of pavement management and add value to automated driving and climate change issues are particularly desired. Big data methods require big data. For example, the traffic speed deflectometer, which is increasingly present in Europe, is a measurement vehicle that collects data on the internal condition of road pavements at network level. Many of these vehicles are now multifunctionally equipped to also collect data on surface condition and the surrounding area. The MESAs available at BASt is such a measuring vehicle, the data from which is used as an example here for BDPave. MESAs records the bearing capacity, the evenness, the surface image, the surroundings in the frontal image, the road geometry, and with the help of a ground penetration radar, looks into the depth of the pavement. Every 10 meters at normal traffic speed, around 60 georeference values are produced. With a usual measurement performance of 400 kilometers per day on motorways, this means that 2.4 million values are available per measurement day. Established evaluation backgrounds exist for some of the data groups, but not yet for others. However, evaluation backgrounds for the linked holistic view of the data do not exist and are the goal of the research to be achieved here. Here you can see a section of the data stock in a table and in a graphic. You can clearly see gaps in the data table as well as peaks and patterns in the chart. Each of these conspicuous features has a reason. They are invalid measurements because of the measuring range was left, bridge structures that differ significantly in their characteristics, local anomalies due to road damage, or simply erroneous measurement results. In order to differentiate in these cases between measurement errors and valuable but interpretable statements about the road condition, expert knowledge is necessary. This process is called data cleaning. The sole exclusion of data rows according to simple rules such as if data cell is empty, then mark the data record as invalid, does not lead to the desired result. So if possible, all cases should be compiled as an exemplary learning sample together with experts. Rules are to be derived from these cases, implemented in programming, and applied via an extended sample. The result is again to be evaluated and serves as input for improving the rules. Artificial intelligence methods are able to derive their own rules from this try and error and the combination of different rules. For the case at hand, this is extremely important as data cleaning cannot be applied manually to the large amount of data we have. It is therefore necessary to map the expert intelligence by means of artificial intelligence. Then the data mining begins. This can also be done with the methodology of supervised learning. Another methodology is that of unsupervised learning. We are currently using this, for example, to find patterns for evaluating the measurement data. The goal is for the algorithms to find their own class boundaries purely based on data by means of clustering. Since this is possible in several dimensions and is linked to various decision-making processes, the method goes beyond the application of purely statistical methods. Fundamentally, however, clustering is still based on mathematical and statistical methods. There are various methods of clustering which we evaluate in the context of BDPave, as well as the best programming languages and libraries to use for this. The so-called k-means method is very popular, and I will explain it now. In the first step, a number of centers which represent the clusters are quantified randomly inside of the database. In the second step, threshold values are set based on the distances of the data points to these centers. In the third step, the distances of the data points to the centers are analyzed, and as a result, the position of the centers is optimized. This is repeated until an optimal and stable result is achieved. With the final distance of the center points to each other, cluster boundaries can then be defined. The methodology thus learns independently to achieve the optimal results. Whether the result is also robust and not a product of chance is checked by means of multiple repetition and evaluation of the result deviations. It is thus possible, for example, to derive a purely data-based evaluation of bearing capacity data for a road category. We have done this exemplarily for a sample of 54 kilometer data of motorway in Western Germany. First, data cleaning was carried out. About 42,000 data sets remained for the subsequent data mining. The result of data mining is the purely database determination of logical threshold values. However, as with all methods, it is important that the results are checked for relevance and correctness, even if only on a random basis. In the case shown here, the comparison was carried out with the assessment values calculated according to mechanical models, and it had a positive result. However, the results can also give reasons to question both the data-based and the mechanically based calculation model. An underestimated instrument for this is the georeferent visualization of the data, but also for the big data analysis themselves, clear georeference allocations are of particular and also underestimated importance. We as road engineers must become more aware of this in the future. This means, for example, that more emphasis must be placed on an unambiguous and accurate documentation of, for example, drill core positions and similar field test data. The challenge with a project like BDPave is to bring together road engineering expertise and the data science expertise. The conditions for this are in place in FEHRL and the FEHRL network. To build up corresponding networks, we have organized workshops to which external companies and institutes have also been explicitly invited. And this network is still in its infancy, and we would be very pleased if you were also interested in supporting the BDPave initiative. Thank you very much for your attention. I will now close with showing you our brand new image video, curtain up for this.
What does it take to make a journey smooth and enjoyable? Most of all, it's the road itself. A good road surface is often taken for granted, but every smooth road is the result of a deep understanding for road construction, management, and interpretation of data. The FEHRL initiative, BDPave, brings together the expertise of 32 road research institutes and their newest scientific findings across Europe and beyond. Working closely with infrastructure owners, FEHRL has access to unique domain knowledge, like construction plan, road condition, and traffic load data. Data that builds the foundation for smart pavement deterioration models that make roads more resilient. In BDPave, we collect traditional and new data sources with cutting-edge technologies to turn big data into smart data, relevant and actionable. Our models will help better predict deterioration of road surfaces so that maintenance measures can be planned and undertaken ahead of time with a minimum of investment, keeping the impact of roadworks on traffic flow low. A smooth journey is something everyone hopes for. Let's create it together. To discuss how you can get involved, get in touch at bdpave.eu.
Thank you very much.